Hi everyone. So in this video, we'll finalize the discussion of noise injection by basically discussing injecting noise to outputs, right? So we discussed before injecting noise to inputs, which is typically considered as a data set augmentation method, and injecting noise to weights. We analyzed it in the previous videos. Now, let's look at what does it mean to inject noise to output. So before discussing the approaches to do that, what does it mean to do that? Let's think of a classification problem for simplicity. So in classification, it means that these training labels given to you might not be 100% accurate, right? So if I am given an image, and then let's say this is, and in training I'm given, let's say it's digit recognition, this is an image of a 1. When I inject noise to that label, it means that, let's say I inject noise with probability 10%, I change the label. That means that these training data, while collection, I believe that there is a 10% probability that the given label to me is erroneous, right? So the simplest way to implement noise injection to outputs is in classification is basically to flip the output label with probability epsilon, right? So with probability 10%, if epsilon is 0.1, I change the output label. Now, if I change the output label, if it's two-class classification, then I just flip it to the other class. But if it's multi-class, let's say in the digit example, and I believe there is a 10% chance that the output is wrong, right? So then if I'm given an image of a 1, with 10%, I flip a coin, 90%. If the 10% side is the one that shows up, then I basically change the label, and then I change it with equal probability among the 9 other classes, right? So with probability 10/9%, I change it to a 2. With probability 10/9%, I change it to a 3, and so on, right? So this is one way of doing it. Another way that's more systematic and really reflects the concept of maximum likelihood estimation is to change the softmax units, right? To change them in what's called soft targets, right? So when we discussed softmax, we said that you have when you combine it with cross entropy, before you combine it with the cross entropy, you do e to the zi sum, right? E to the zj and all the j's, right? And we said another way of looking at this is basically where I is the label given to me in training, right? So this is the training label, right? Another way to interpret this equation is basically that you take the vector z of output units and you multiply it by a one hot vector, one hot encoded vector, right? Representing the training label. Meaning that what? If it's an image of a 1, then I have a vector of all zeros, and then in the index corresponding to class 1 has a 1 value, divided by sum all the j's e to the z transpose yj, right? So this is the regular softmax, right? So you take the vector corresponding to the output units, you have a dot product with a one hot vector representing the class label, and then you divide by the sum of doing that for every other for all the possible class labels, right? And I here is the index of the training label. Now, instead of doing that, when I add noise injection to the output, I basically change the 1 in the one hot vector. So instead I have a vector of zeros, 1, and then zeros. I change that into a vector of epsilon over k minus 1 instead of the zeros, and then 1 minus epsilon instead of the 1, and then epsilon over k minus 1 instead of the zeros, where k is the number of classes, right? So if epsilon is 0.1 and I have 10 classes, then I change the label given to me in training to 0.9 instead of 1. I replace the one hot vector by a vector that has 0.1 in the index corresponding to the training label, and has 0.9 in the index corresponding to the training label, and 0.1 divided by 9 in all the other indices. Now, this is actually pushing the output units. Instead of pushing to have a 1 zeros, you push for that new vector, right? So training will push towards having the output units represented by this vector. And this reflects maximum likelihood, because this is actually the probability that you want the network to present. That if I'm given a training label with image 1, then I want the network to represent a probability distribution where the output in this case with probability 90% should be a 1, and with probability 10% equally divided among the other classes, it should not be a 1. Sounds good? So this is actually much more effective, especially, typically much more effective, especially if the training set is small, right? Because what I do when I flip the outputs instead of changing the softmax is basically as if I'm doing that same distribution but empirically, right? And the empirical distribution approaches the true distribution if the number of examples is large. If the number of examples is small, right, then this approach is safer, as it reflects better, or more principled, let's say. It reflects better the maximum likelihood estimation. But it's slightly more complicated than the approach of just flipping the outputs. Thank you.